So a very warm welcome to everyone. I'm Gordon Blair. I'm part of the ensemble team that's hosting the Entangled Festival. A really great welcome to this chat, this conversation, which will be hosted by Steve Hallett. This is part of a series of conversations. There's this one on Monday, there's one on ecosystems on Wednesday, and then there's a final one about art and research on Friday. So Will's going to paste into the chat in a second, and if you really enjoy this one, you'll come back for the other conversations. And I think that's all I want to say. I'm going to pass over to Steve for what I think will be a really fascinating conversation.
Fantastic, and hopefully you can all hear me. And a very good afternoon to everyone. It's very good to be here. Thanks very much for your introduction there, Gordon. I think this is part of the wider Entangled Festival, which goes on until the 26th. And looking at the program, there's a whole range of absolutely fantastic events taking part in that. So I'm delighted to be part of that action. It's very good. Thank you very much also to colleagues behind the scenes who've helped to make this happen. So as Gordon says, I'm Steve Hallett. I'm Chair of Applied Environmental Informatics at Cranfield University. And I'm also one of the NERC digital environment champions. And so I'm fascinated by all things to do with digital technology as it applies to environmental science. And that's very much the focus of our conversation. And I'm joined by some real experts to try and untangle the themes around that. And you know, one thing we know about the world around us is it's extremely complex, many interdependencies, all sorts of linkages between things, and trying to unpick these complexities in terms of understanding scientific processes, but also in trying to help policymakers make rational decisions about the environment. We need tools that allow us to make that action possible across all the different biota, from the polar regions to the oceans to the land and the atmosphere, of course, as well. And what we're interested in very much doing is drawing across an arc, if you will, of technologies. At the one end of the arc, we have sensors that are out there in the environment, as we'll hear, in some quite hostile environments, gathering raw data. The arc carries on as data is captured, data is preconditioned, processed in some way, transported through to mechanisms for holding data. We hear about data lakes, obviously databases and so on. And those data together form the inputs for subsequent analyses that we undertake. Computer models, machine learning, the use of artificial intelligence techniques. And those outputs from those sorts of analysis are used to feed presentations or visualizations of data which help scientists and policymakers understand that. So I'm joined by four real experts in this area, and hopefully you'll share with me an excitement about the range of the breadth of scientific work that they're undertaking, and we'll hear more about that. I'm joined by Professor Jane Hart from the University of Southampton, whose work in glacial environments, capturing data in quite hostile environments, is quite fascinating. I'm joined by Matt Fry from the UK Centre of Ecology and Hydrology, the CEH, and his work and his team on national scale sensors looking at river conditions and soil conditions is key to understanding big scale environmental science. We're very lucky to have Dr. John Sidon, who's Associate Director of Digital Oceans in the National Oceanographic Centre, and his work on capturing the data from the many sensor platforms that are operating out in the oceans, feeding oceanographic science. And John's interest is in digital twins, something I'm hoping to come to. And we are joined by Dr. Jenny Brown of the National Oceanographic Centre as well. Her work is very much on trying to understand the role that technology can play in supporting societal understanding of risk and societal change and supporting decisions in an evidence-based manner. So if I could start really by inviting Professor Jane Hart to join me. If we were on a stage, of course, we'd have that pop up Jane, and we'd be sitting next to each other on a comfy sofa and so on. But here we are in COVID land online. It's very nice to see you again, Jane. I hope you're well. Thanks very much for joining us. So, I mean, maybe we could just start actually by, if I could just ask you to tell us a little bit about yourself and your science and what's led you to be motivated by all things digital. So,
right, okay. Well, hi everyone. Lovely to be here. As Steve said, I'm Professor of Physical Geography at the University of Southampton. I'm both an expert in glaciology and informatics. I'm very interested in how glaciers respond to climate change. So we know that as temperatures warm, so the glaciers melt and that water goes into the oceans and causes sea level rise. But the trouble is, it's not a sort of direct relationship. You can't say X% warming will lead to a certain percentage of millimeters rise. It's a lot more complicated than that. And that's because we don't really understand what goes on at the bottom of the glacier. And so this is really why we have been devising instruments to sit down at the bottom of the glacier, try and understand in real time what's going on. So I was involved in a project called GlaxWeb, and I've got here Exhibit A. So this is, oh yes, you can see it. So this is what we devised called the probe.
Oh, yes.
You can't probably see that in the camera so well, but it's about 16 centimeters, and it goes down to the base of the glacier. So we drill a hole in the glacier using hot water, release these into the bed of the glacier, and they send back their data live through an ingenious way back to the UK, and you can look at it online. It's not currently working anymore, but it was working, and it was the sort of first project that did that. And that is really exciting because these sensors allow you to understand things for the first time, because the subglacial environment is one of the least explored environments on Earth. And I'll just illustrate one thing about winter. Most people think that the glaciers sort of don't do much in winter. And before these studies, it was very difficult to know what was going on in winter, but because these send back data all year, now we have a kind of really good pattern. We now know what's happening during the winter, and it's completely turned over. Just a few basic ideas like that.
I guess the sort of sensor you've shown us is a bit difficult to go up and change the battery if it's buried in the glacier. I mean, how long do these sensors last for when you deploy them?
The longest one lasted for 2 years, which we were very pleased about. Obviously, you can't go back and get them because they're buried sort of 70 meters deep, so you can't retrieve them.
And I mean, and they can transmit radio signal back to base, as it were, can they? That's
yeah, they send their signal back to the surface of the glacier, which is about 70 meters, and then forward it on by different ways to the internet.
I was fortunate enough once to stand on a glacier, and I was struck by the unairy sounds coming up from the ice beneath us. And so, of course, I was wondering what sort of things are you measuring? What sort of things are you recording in the glacier?
Well, we'll point out that every glacier is different. They're all exciting. We're measuring. We're trying to get an idea of what's going on there. So we're measuring water pressure, temperatures, the conductivity to know if it's water or sediment that it's resting against, and tilt, in particular tilt, because when it's in the sediment beneath the glacier, they're moving with the glacier, and we were able to get the first study of actually in 3 dimensions because they initially go in like this vertically, and then they're pushed over with the ice, and then they actually rotate as well. So huge amount of laboratory studies have gone on about how bodies move in a viscous material. And of course, this is actual sort of real life physical examples.
So you've got an axiometer or a gyroscope or something in there that can tell which direction it's being twisted. And fascinating. So, I mean, what sort of length of, I think we're going to hear perhaps from Matt in a bit about putting in place, and John, national sensor networks. I mean, how many, if you were looking at a particular glacier, how many sensors would you typically have to capture what you need to know about it?
The reason that's a difficult question to answer is because, how long is a piece of string?
Yes.
Because we know virtually nothing about what was, before the project, about what's going on down there. Any information is good. These are telling you a lot about temporal changes, and as many as possible are good, but they're very difficult to put in. They're very difficult to make. And so I think at any one time, we never had more than 5 operating. Obviously more would be better, but it's telling you amazing data about temporal changes.
Absolutely. I mean, I suppose the other thing is it's easy enough to rock up to a tree and stick a sensor on it, or dig a hole in the soil and drop a sensor in. But I mean, actually getting up on top of a glacier is quite a feat, and it's a very hostile environment as well. So how do you go about designing your research and also the sensors to be robust enough to, you say they last two years with a battery, but I mean, surely they must get bashed to bits by the moving ice and so on.
Yeah, so we, like everyone builds on the scientists who've come before them. Before we did it, the instruments were sort of loose and on wires. So we have encased them in this quite solid plastic case. So that protects the sensors that are in here. And the size is designed specifically so it will go down these holes that you drill with hot water. So actually, in some ways, that's the hardest thing. The hot water drill weighs about 200 kilograms. So you have to either drop it with it, well, not drop, but put it with a helicopter, bring it in with a helicopter. Or in Iceland, they drive it onto the glacier because they've got these super 4x4s with, they let the tires down and drive on the glacier. So it's quite difficult to get the instruments on, and then you have to drill and then you put them in. And obviously building these in the first place, it takes an incredible amount of effort. So it's not easy to do.
I mean, what's interesting then is the sort of the evolution of the technologies that you're using, and you're quite rightly saying you're building on the work of scientists who've come before you. But what's your sort of impression of the changes that are on the horizon really for this sort of science? So where's this sort of heading?
Well, the big problems with this are power and the communications. So over the years that we've been doing it, everything has become more miniaturized, and the battery powers are getting longer. So those are the sort of changes that we're seeing. I mean, we'd like to make it smaller, because then it would presumably act. But the idea is it is supposed to be like an actual stone, and you do get stones this size. So so that's okay from a point of view, but it probably would be nicer to be slightly smaller. And as time goes on, that's possible. Okay. So there's a big new change, which is called the Internet of Things. And that's where each of these elements that you put in have their own IP address. So they have their own website. And that's a more standard way of doing things.
Right. So that's probably the shape of things to come. I'm just conscious that colleagues out there in the audience may have some questions for Jane, and feel free to pop questions in the chat, which I'm just looking here to see if there's any coming. So do add some questions, and while we're waiting, just in the spirit of the festival, of course, Gordon was extremely anxious to know that typically if we were sitting side by side on the sofa, there'd be a band playing as you walked on to the stage, and so Gordon was very anxious to know what your theme tune would have been and why would that have been the case.
Right.
While you answer, let's have some questions for Jane.
Right, it's going to be Chameleon by Herbie Hancock, which is from the 1973 album Headhunters. And I've chosen this because I'm a great jazz fan, and this is just such an upbeat tune. And I think that at the moment there's so much news about the environment, it's so downbeat, gloom and gloom. But this is something that's very positive, and hopefully you can't listen to it without tapping your feet.
I can imagine you there on top of the glacier with your headphones on, or being lowered down from the helicopter. So thanks very much, Margaret. There's a question here. So how does the sensors transmit the data actually through 70 meters of ice? Just perhaps if you could just reiterate how that works.
It's radio waves. I'll look up the details for you, but it's a low frequency radio waves can get the data through. They're specifically designed so that they only turn on for a short time, so that they don't use their battery. So they only send their data and collect their data for a very short time, so that they last as long as possible. Perfect.
Well, Jane, thanks very much. That's absolutely fascinating. And Margaret, thanks for your question, and do keep them coming, folks. I'm just wondering if with another drum roll, we could perhaps invite the second of my guests this afternoon, Matt Fry from UK CEH. Hey, Matt, how are you doing?
Very well, thanks. Thanks for the intro. First time I've been introduced with the drum roll, I think.
Well, don't worry, we'll get to your theme tune later on. But no, it's very good of you to join us as well. And listening to Jane's talk about placing these sensors in these quite hostile environments. Now, your own work involves building large networks of sensors of all kinds of environmental projects, and I wonder maybe if you could just give us a bit of a overview, Matt, of your work and how you are using digital techniques to advance your scientific work.
Thanks. Yeah, well, thanks for the invitation to be here. It's great to hear Jane's talk, because I started my career doing my master's with a dissertation on a glacier in Iceland, trying to measure it with radar. I know all that great introduction to the kind of messiness and difficulties of environmental data, and the kind of importance of getting it, making it available. So yeah, like you said, I work at UKCH. I've set up networks. I've worked with lots of huge teams of people where I kind of lead on the data management side of things. So this is national archives of river flow data that we bring in from the Environment Agency and people like that. And we run our own monitoring networks as well. So in particular, the Cosmos UK soil moisture network of sort of 50 sites around the country, streaming in real-time data. So the main interest to me is really just making sure that data is as useful and as used by as many people as possible. So I've been doing this sort of work at CEH for kind of 20 years, making sure the data can be embedded in research, can be understood by researchers, can be accessed easily, can be found. And yeah, there's obviously been huge amounts of technical innovations over that time, enhancing the way we can do that. And yeah, it's just trying to harness those and bring them in and make environmental data as useful as possible.
You mentioned the Cosmos network. So of course, this is using satellite data to look at the ground conditions. Is it?
Not exactly. It's actually it's an in situ network. It is ground. They're ground measurements.
Yes.
But they're field scale measurements, unlike the kind of point probes that you put in, which are very sort of very affected by the kind of inevitable homogeneity of the heterogeneity of the ground, the soil conditions, where it's measuring soil moisture exactly one tiny point is very difficult. These give a kind of averaged measurement across a kind of field scale of tens of meters of radius, and yeah, they work by some black magic whereby cosmic neutrons come down from space, and they collide as they come through the atmosphere, release other neutrons of certain speeds, and they are absorbed by water in the ground, and you can use that as a kind of proxy measurement then for the number of neutrons that you can pick up is the kind of inverse of the amount of water in the ground. There's a hell of a lot of adapting and calibrating that data, taking account of background, humidity in the atmosphere, and all sorts of other aspects, as well as the background radiation, which we have to bring in data from the top of a mountain in Switzerland, which luckily is available online.
Oh, yes.
Allows us to do it in real time. So yeah, but so we've got this network of 50 sites with also really good meteorological stations there. So there's a whole range of data for people doing modeling at those sites. But the field scale nature of the measurements makes it particularly useful for validating the satellite data, because obviously they're coming down to the kind of kilometer, hundreds of meters scale, those satellite footprints, and it's very hard to calibrate that with these point sensors. So having this kind of average field scale measurement at quite a few sites, different land covers, different soil types, is really useful for those satellite measurements.
So there's a sort of a statistical approach really to ensure that you have a representativeness of the data you have across the different landscapes of the areas that you're looking at. Yeah,
it's difficult. I think it's nice to think you could kind of plan a monitoring network purely from a statistical point of view, but there are so many practical considerations like landowners and actually finding the soil types, as well as the variability of the soil moisture. So our network's kind of, if you see the map of it on the Cosmos UK website, there's much more dense in the southeast and much less in the northwest, where we kind of expect soils to be wetter a lot of the time. The technology's effective in different ways on different types of soils as well, so there's and different conditions. So it's a mixture of representativeness and practicality, I suppose.
Maybe you'll share in a minute the link to this, and then folk can follow that up and have a look.
Yeah,
I'd be interested. Another sort of quick question then. You mentioned the National River network as well. What sort of things are you measuring there, and what's the sort of density of measurements you have there? There's a lot of rivers on the, the UK.
Well, you think we do a lot of international work as well, and really we have very small rivers compared to a lot of the world.
Yeah.
But if you look at the density of our network, it's really quite phenomenal. We do some work in countries that are multiple times the size of ours, and have got really tiny fractions of the number of stations. But so there's been a need in the past for good quality river flow data for water resources assessment in particular. And that was the kind of key mandate a long time before I started of the National River Flow Archive, to take daily flows from people like the Environment Agency, which were at the time quite painful to produce and process up to daily value. So that was the focus. That's been the focus, and that's the kind of key useful data set for water resources modeling. There's another kind of data set around there around statistical flood peak data, annual maxima and the number of actual peaks, and that's used in lots of statistical methods for estimating the kind of return period of a 100-year flood, for example. So there's two kind of key data sets around that. But the interesting thing about that, and something I'm really keen on taking forward, is the fact that those are the kind of final output measurements of a whole system of measuring. Well, they start with often measuring the water level, and then there's a kind of calibration rating, it's called, to convert that to flows. But that water level data isn't necessarily widely used by researchers, because it's a bit more tricky to use, because there may have been changes in the structures over time and the water levels might not be the same. But there's potentially a huge untapped resource of information there. And another data set now is, I mentioned these rating calibrations between levels and flows. Those are based on sort of spot measurements over time, and you draw basically a curve between those points. Nowadays, those used to be made with a kind of little propeller on the end of a stick by measuring the flow. But nowadays, those are measured by Doppler instruments that you put on a little boat and send out across the river. And as well as giving you the total flow across the river, they actually give you really detailed increments of the flow throughout that cross section, potentially the sediment concentrations in the water flowing through there. They give you the bathymetry of the river in that point. And again, there's a huge untapped resource of data that the Environment Agency have been making these measurements with these boats for years now, but that data is not necessarily accessible. So it's something we're really keen on trying to see if we can bring that.
Is that something that some of these digital technologies that we use now, that we're starting to bring in, can actually help with that? I mean, I was going to say one of the advantages of the sensors and digital techniques is this data can be made available almost in real time to scientists building their models and so on. I mean, what do you see as the sort of future directions for the sort of work you're doing?
Yeah, I think integrating the data and making it more readily accessible in real time is a real key thing. Data like that, which is taken out in the field on a boat, as soon as they're back in the lab or whatever, that could be uploaded. There's a whole load of processes need putting in place to kind of to make that data available. That's potentially really interesting because it's a reasonably large volume of a very specific data type that not everyone might be able to use. But there are these virtual labs and things that you could imagine, a data archive of this data with online tools that you could analyze that data and produce these images or data about the sediments in the transect at that point, without everyone having to be an expert in how do I transform this data, what do I do with this data. You can have those open source and shared tools that allow everybody to do these things. And the other aspect is the integration. So data streams coming in, we can see, you could probably find online a water level measurement in real time and a temperature sensor somewhere from the Met Office or somewhere else. But actually pulling that data down, putting it together and doing something with it is actually really time consuming and painful still. So there's issues around just understanding what that data is, finding where it is, having it in consistent, well, we say formats, but really it should be
streams
of data over the web that are describing that data in the same way, giving the information about the sensors used. And I'd say I guess a couple of the key barriers that we want to break down is getting uncertainty information. So there's people who make those measurements and instruments and deploy them. They know the uncertainties in them, but that doesn't kind of come through with the data very, very rarely.
Right.
That could be embedded in these streams of data. People could, research tools could make use of that on the fly as they use it.
So we need better metadata, it seems. Matt, let me just have a quick turn to the chat board and see if there's some questions coming in. And I see Bill, thanks very much for your question. And Matt, Bill, if I understand your question, the development of various phone apps that use river photos and cross sections to measure flows and velocities, and just wondering whether those sort of apps come into your work and whether you're using that, and whether that gathering, let's say, socially gathered data is possible in your work.
Yeah, there's all sorts of developments in that area at the moment. There's a technique called flow velocimetry. So it's using videos there are bits of software now that you can just download. You can run them on your phone even that actually convert an image of something, a moving stream in this case, but probably lots of other things. You can probably use them to monitor the speed of the traffic past your house, and convert that into velocities at the surface. And as Bill says, with available, and we've got LiDAR coverage coming at 1 meter scale over the whole of England come at the end of this year. And we could bring those things together so that you could automatically get the shape of a valley in particular outside of the stream, in particularly important for out of bank flows, which are rarely captured well at gauging stations, which are built for containing the stream. But as soon as it spills out across floodplains, it's very hard to measure. So those sort of technologies can be really useful. And we've got a NERC project at the moment to scope out a potential flood and drought research infrastructure, they call it. So trying to work out what technology could deliver the hydrological measurements that might really advance science. So we're kind of building up ideas around those things as we speak.
Matt, I see Jane is clacking away a number of responses to folk about glaciers. Jane, I wonder if you'd like to hop back in and well, I've got you both. I mean, so we've heard a lot about sensors. I mean, what, really a question to you both. What are the sort of pitfalls that you face when you're trying to put in place environmental sensors, whether it's on top of a glacier or a river, or indeed in a sort of terrestrial sense? What are the sort of pitfalls that you grapple with? Who'd like to go first?
That sounds like a question for Jane.
I think that for us, the challenges are really about this power and the communications, because the whole time it's about, you'd like to capture as much data as possible, but you have to be realistic. So so in Iceland we were collecting it once every 4 hours, because that was the sort of best mix between it lasting a long time and yet trying to get these temporal changes. And what we'd love to do is to have a system where if an event happens, so like there was suddenly the glacier shot forward because it was warmer, there was rain or hot day, then we could record it more frequently. But that's something that we weren't able to do. I think that's kind of in the future that you could do that, sort of this sort of clever, smart sensing. You sense more when you predict an event is going to come, perhaps from a weather prediction or something like that. That would be nice to link the two.
I'm interested to see your response to the earlier chat. Presumably you've got some sort of inertial sensors in the device that can tell you how far it's moving, but 40 meters a year is in one of your experiments, was it?
Well, 60% of that we were trying to work out how much the sediment underneath the glacier was moving with respect to the surface of the glacier. Yeah. So yeah.
Well, Matt, what are the sort of challenges looking forward then? Digital techniques are being used clearly in environmental science, and here we've seen some very nice examples of that. But what are the challenges looking forward for these sort of approaches?
So, well, just thinking about data itself rather than how people make use of the data. It's really good to hear Jane's comment about IoT earlier on, and the seminar series that has been running has been really great in that sense, to learn about some of these technologies. And I think it would be, Jane's team she's got a team of experts who know about that whole telemetry and the sensing and the broadcasting of the data and the management of that data. And I think it's trying to, there's a huge amount of opportunities in this deploying, people being able to deploy new types of sensors and different types of sensors, but it's not always the case that teams are going to have that whole range of expertise. So I'd really like to kind of think about how the research community could be enabled to focus on the measurement and the sensors, and we could support the delivery of that data, the management of that data, streaming that data into places that it's accessible to themselves, to the researchers, accessible to other people, able to be integrated with other data sets.
Yeah.
And something else.
Sorry, Mike, go on.
I was going to say something else we're working on is the quality control. Then if you've got one sensor and you're looking at it in detail, then it's you've got the time to manage that data. But when you've got a large network of lots of sensors, you have to start thinking about automating that quality control. So we've been looking at from simple automated processes up to starting to look at kind of machine learning so that you can build up relationships between data streaming in from one sensor with data from other networks, just not as a way to kind of automatically, sensor, take data out from that, but at least to flag up to people where there may be problems with that data if it's, wildly deviating from what you might expect.
I mean, maybe a sort of question to you both, really, looking at Daniela's question. Thanks very much for that. There's clearly vast untapped applications of the data that you're gathering. Jane, I wonder if that's the case with your work, but clearly it sounds like it is in your case. What sort of local hierarchical intelligence, Daniela asked, could help with that, and what sort of insights do you might have as to how you might approach that? I mean, how can you help people find these untapped hidden uses of data, and combining perhaps glacier data with meteorological data from somewhere else and so on? What for new applications?
Who's that to? Sorry, Stephen, I missed that.
Well, I mean, probably both of you, really. Let's start with Jane. I mean,
okay, I'll make a prediction that we can't do it at the moment, but maybe we can do it in 10 years' time. The difficulty is having things sort of live, combining these different data sets. They're hard enough to get them at the moment, but I think that is the next step. And I think I'll make a little push for training, because young people starting their PhDs, it's very important that they are not particularly taught specific programming or something, but they're taught this sort of open-mindedness that everything's changing so fast that you need people that can adapt quickly, and they can learn something and then learn something else. Because, when I was a postgrad, you didn't have a ground penetrating radar that an ordinary person could use. Going back to that, you had to be an expert, but now anybody can, relatively anyone can use it. And it's really vital for glaciology. So, technology moves on quickly all the time. You need people who are flexible and can change and learn new things.
Yeah, so super point about training there. That's very important. Matt, I have one last question for you, but sadly it's not to do with data. In the spirit of the festival, I'd wonder if you'd like to untangle yourself and advise us what your theme tune would be.
Oh yeah, no, I'd love to come down to a theme tune one day. I was thinking of tunes that have water and river flows in them. And anyone who knows me knows that I'm a big fan of the band The Fall, and they've got a song called Mountain Energy, which I think suitably captures the mood.
Well, there you go.
I recommend a listen to people.
Super advice. I mean, just a note here. Thanks very much indeed to the everyone who's listening, who've been posting a series of excellent questions. And obviously we can't answer them all, but I wonder if I could invite Jane and Matt to just continue and maybe address some of those questions. As if it's all right, we'll move on to our next guest. And so I'll say goodbye to you both for now. And welcome to the stage with a large drum roll, Dr. John Siddon, who's Associate Director of Digital Oceans at the National Oceanographic Centre. And John, a very warm welcome to you. Thank you very much for taking up some of your time to come and talk to us today. It's very nice to see you again.
Yeah, afternoon, Steve. Yeah, nice to see you.
Looks like you're actually in the office there, which is it's good to see after the.
Yeah, 6 months in, and I've got a staff pass, and I'm actually in a building. Yeah, fantastic.
Yeah, so you're.
And I can see the Discovery just outside, by the way. Possibly you can turn the camera.
Swing your camera around and show us in a minute.
Yeah.
So you're sort of bedding into your new role there as AD and in the NOC, having come from the Met Office. So I think you'll have some very interesting sort of perspectives about digital environmental science and the digital environment. But maybe we could just start, if you wouldn't mind, just give us a bit of a background to yourself and your career and your interest, and what is it about digital environment that I was going to say float your boat, but I don't think that's appropriate.
Hopefully the boats float for sure. So my background is, as you say, at the Met Office, and my career has been, to date anyway, in ocean modelling. So as a researcher, I started off developing various ocean models, and then providing services on the back of those models on the basis of assimilating data into the models to provide forecasts. So both forecasts for sort of short range information about today, tomorrow, for waves and so on, but also initializing the ocean state of today for seasonal forecasts and doing reanalyses. So there's a lot of work in the data assimilation world, which is actually quite similar to a lot of the data sciences activities around machine learning. So data assimilation is the art of taking an observation, in my case from the marine environment, minimizing a cost function, understanding the errors in the observation and the errors in the model, and then coming up with what you'd consider to be the optimal real state. So having done that in the Met Office, it seemed like a logical extension. So the National Oceanography Centre are looking to work more closely in the area of, I wouldn't say in data, because the data is really sort of at the core of what the National Oceanography Centre does. We have 2 ships. We also have a whole load of autonomous sensors. The Internet of Things has already been mentioned. Yeah. Essentially, we do the Internet of Things within the ocean. But bringing the data, the science, and the data sciences together is kind of where I'm trying to work. And so the concept of digital twins is really a concept that kind of encapsulates.
Yes. So it sounds like there's a lot of learning and crossover from your work in the Met Office to the NOC. And it's interesting that presumably many of the techniques and approaches are equally applicable in the two sort of theatres, as it were. So you're able to bring across those experiences.
Yeah, certainly, and as I think Jane, you mentioned skills. I think there's a real challenge in the environmental science community, bridging the gap between the sort of the science skills and the digital skills we really need to make best use of our data, and that was something that the Met Office has perhaps confronted slightly earlier than maybe the rest of us because of the operational nature of the work. So I think there is an awful lot of understanding how you manage data effectively that we can learn from that operational environment. But then taking it a step further, taking it to the point where we can really maximize the knowledge in our big data, because data is going to get extremely big, particularly in the ocean. And so we need different skills. We can't just be using Excel spreadsheets. It's just implausible. So we've got to learn different skills to really do the science we want to do.
I remember somebody in Microsoft once informed me, and when asked what the definition of big data was, they said, well, it's when Excel can't cope anymore. That's big data. It's from there onwards.
Yeah, which means pretty much everything these days.
Yeah, exactly. Yeah. So I mean, you mentioned digital twins. That's something I'd like to come back to in a minute. But maybe before we do, so you're also responsible for one of the data centers in NERC, and there's 5 of these data centers. I mean, what are the sort of challenges when you're receiving these vast bodies of, in your case, oceanographic data, for some of the issues that Matt so eloquently described earlier? There's the importance of the metadata, handling uncertainty around that. What are the challenges that you're faced with trying to receive and process and handle and then get back out those sorts of data sets?
Yeah, so I think there are a number of challenges. One is technological, is building the infrastructure, the technological infrastructure to manage the data, and that's clearly a big challenge. There's also a cultural challenge. I think as scientists we're quite used to collecting our own data, and it's our data, and I think managing that on a case-by-case basis doesn't really work very well in the modern modern informatics world. So sort of trying to create best practices and the uptake of best practices is really key. And then using new technologies to do things like post-processing and making sure we get the maximum value out of the data. I think particularly in the ocean, and it's true as well as in the glaciology, that the cost of getting data is so huge, and the difficulty of getting the data is really paramount that we get the most value out of it. So the challenge really is to make each piece of data really valuable, or as valuable as it can be, so that we're giving good value to people.
And we've I suppose we've been discussing this idea of lots of applications that the data could be repurposed for, and in some ways we can think of new ways of using the data as well. Now, talking of new technologies and coming back to the earlier comments you made, and we keep hearing this phrase digital twins coming out, and when I first heard the term, it was something coming from the aeronautics and the defense sector and other engineering fields and so on. And so first of all, give us what is a digital twin to you? What is a digital twin?
Yeah, it's often quite an unhelpful phrase, isn't it? Because people perhaps interpret it slightly differently. My understanding of a digital twin is that you essentially have 2 components: the digital element and then the physical element, and the 2 things are as close as you can make them the same. Depending on what the problem is, of course, your digital element will have different features and so on. But the key fundamental element is that you have observing networks within the physical element that inform your digital representation of the truth, and then your digital representation of the truth allows you then to influence somehow how your real world, your real twin responds. So in a built environment, that's quite easy to sort of envisage. So you can turn your central heating up and down based on measurements that sort of control your building. In the ocean, it's perhaps less obvious where that feedback, at least in the real time, which is what most people consider to be digital twins, how that might work. But there are plenty of examples where it's important. So we're thinking about the sort of the research ships of the future. And one of the things that's very obvious is you could have an information grid around the ship where the data you're collecting whilst you're at sea is informing your decision making about where to place your sensors next. And so your physical environment are your gliders or your instruments, and then your digital representation of that allows you to repurpose where they're going, and therefore get maximum value out of your observing network. That's one example, and there are plenty of others we can think of.
Yeah, absolutely, and I think each of the guests here will have perspectives on that, and I think that's something maybe we could come back to at the end and just see what other folk think in their own areas. John, I see there's a few questions flying in here. I'm just trying to disentangle. It seems appropriate. Which ones are actually for you, and which ones are sort of more wider? And thank you to Matt and Jane who've been busy answering some of the other ones. Let's see. Bill, was your question? Is that related to Matt's? Yes. I mean, there's certainly a point which. Yes. So one of the big digital twins that we hear about is the sort of digital twin of the planet, or digital twin of the Earth, or DTE as it's sometimes known, which is very ambitious, trying to capture a whole holistic view of the planet Earth. Are there scales of digital twins that you could think of? I mean, you're talking about sort of small parts of the oceanographic circulation, or certain aspects to something like a DTE. Where's it going?
So yeah, that's an interesting question. So I think of them sort of three different scales of digital twin. I think you've got the planetary scale, and clearly you're not going to be able to represent the planet at at sort of microscopic level, but you can perhaps do it at the kilometric level, and that would be very useful for global scale problems. But of course, when you get down to specific problems like the one I mentioned about guiding your autonomous vehicles around a ship, for example, you're talking about tens of meters rather than kilometers. And then I think there's an intermediate scale. So what happens, for example, in the context of coastal hazards? I think something at the sort of the national scale, the UK scale, or looking at marine protected areas is another area we're thinking about. So a marine protected area could be a sort of 1,000 square kilometers. Having something that monitors and then feeds back the ecosystem health in an MPA is at an intermediate scale between the global and the very local. So I think there are examples at those three levels. Perfect.
John, I have to ask you, as I will ask everyone, what is your theme tune and why?
Yeah, this is one of the most fun things I had to do for a panel. So I thought about this quite hard, so I quite like Björk, partly because of my Viking background, and she's got a song called Human Behavior, which I really love. And I think a lot of what we're trying to do and what we can do out of these digital twins is learn how to unmask the environment in a way that people can actually engage with. And perhaps this is a route for us to sort of try and influence human behavior, because I think it's very important for us as environmental scientists to understand what it is that we can do to make people understand that our environment is fragile and that we need to change the way we're interacting with it to make it better.
That's a very nice moment, I think, if I may, to bring in my fourth guest, Dr. Jenny Brown, who's a colleague of yours as well, John. So perhaps bring you back in a moment. Hello, Jenny. So I think you're just muted, are you? Or I can't hear you just at the moment.
Hi,
there
everyone.
we go. Super job. Well, very good to see you and hear from you. Thanks very much for joining us. And I think John was just raising a very interesting point there about the role of technology in helping society understand some of the challenges that go on, and that very much characterizes a sort of key plank of your work in terms of flooding and flood risk and the rising sea levels and so on. And you also work in the NOC, the National Oceanographic Centre, and you're also, as with the other guests today, a member of our expert network panel. But I wonder if you could just give the everyone listening a quick overview of your career and your background and your interest in digital environment.
Yeah, no problem. So I kind of fell into digital environment. So I always wanted to be an oceanographer. So I got a job at the National Oceanography Centre working with computer models. And of course, when you start predicting environmental processes, you start realising you need observations to validate these models. So I was involved in looking at flood risk, erosion risk, and you can get lots of validation data in the ocean, waves, water levels, tides, weather data. But what we're missing is observations actually at our coastline where the water comes over our sea defences. So more recently, I've been looking at new technologies to capture information about the waves that come crashing over our sea defences. So that's what I'm working in at the minute. And because this information is also very important for forecasting and real-time response to flooding, this is when digital has started to come into my career, as I've realised we need to be able to nowcast this data.
Yeah.
I've been working with the British Oceanographic Data Centre to ensure we gather information in near real time and actually get it onto public websites so other people can then build downstream services from it.
Now, Jenny, you've just used a word there, which I'm afraid you're going to have to explain for everyone. Nowcasting? What do you mean by nowcasting exactly?
Ah, yes. Well, so I had to work this out as well when it was a term that suddenly started being used more and more. So forecasting, people probably are familiar with. We forecast what might happen so we can plan and prepare. So in the world of oceanography, maybe that's shutting the Thames barrage when we know there's a surge going to occur with a large tide. But nowcasting is getting that observations in near real time to kind of nudge our models and what our prediction is for what's really happening. So if we think about perhaps river flooding, a river model might be able to predict a flood event, but if you've got debris in a river, that model might not know where that debris is in real time because it's probably got the riverbed, the rainfall coming in, the groundwater coming in, and then where the flood water is inundating. So through nowcasting, if you can capture extra information as it happens, you can then start to adjust your predictive capability and better respond to an event as it unfolds.
So you're sort of almost recalibrating the model in real time with extra additional information that's come in to sort of really reduce any error or uncertainty in that. That's interesting. So
I'm not sure where the difference is between data assimilation and kind of nowcasting data into a forecast service. So that's where it starts getting a bit confusing.
Well, that's a question we can put to colleagues as well in a minute when we all come back together. But I'm thinking you've mentioned forecasting and nowcasting. Of course, the other one in the sort of the trinity of these is hindcasting as well, where one's sort of almost looking at data that's been captured and rolling the models back to see if the outcomes that the models will predict is broadly the same as what actually happened, and if it isn't, then why not? So you have this sort of ability to look forward, to look now, and also to look backwards as well. It's an interesting approach. So Jenny, some of your work involves very much capturing the enthusiasm and input from members of the public as well. I mean, I think I've seen you posting photographs where there's a socket where you can put your mobile phone in that takes a picture along the coastal region, and you can upload this picture, and then slowly but surely you'll gather a vast body of citizen science data, I suppose, and very cleverly you have this bracket sort of fixed in a particular way. What do you think the sort of role of citizen science is in supporting some of these sensor driven sources of data we've been hearing about? Do they balance each other out, or what's the opportunity and the threat, I suppose?
So citizen science can kind of have different roles. So what you were initially describing was the International Coast Map programme, where there's a cradle for your phone at the beach. People post their photos online, And then the photos are processed to be able to predict the variation in beach level. So we've got early warning of erosion risk. But also people can be contributing data without really knowing it. So in a recent project, I used photos on Facebook to plan our field deployments. So when we wanted to go to the beach, I looked back through a record of photos that were on a site that was called I'm at Crosby Beach and the weather is ... Then there were lots of photos of sunny beaches, stormy beaches. So I found all the photos when the waves were coming over the seawall. And I could then look at observations to see what the conditions were like. So I could then plan using weather forecasts when to go to the beach with our equipment. So social media is a great way to collect large records of what's going on in the environment. It provides us with actual visual evidence, which is very useful, helps us plan our research. And then citizen science in more targeted applications also add extra information. So we don't have sensors everywhere due to the cost of sensors. So when we can use low-cost methods, get the public involved, that really does help broaden the amount of information we can gather at our coastlines.
That's really interesting. So you're almost differentiating active contributions that people have made and then almost surrogate data that you're able to infer from data that exists. I mean, I know the Environment Agency, when they've been looking at flood response modeling, have investigated the use of Twitter images. People take a picture of, look at the flood coming near my house, you know, and there's a photograph, there's a timestamp, there's an evidence point there. And sort of if you have a situation room where you're trying to really understand what's going on, that could be a valuable source of information. But there's probably pitfalls in that as well. If you're doing keyword searches, you have to be careful. All sorts of unintended consequences, I guess, of searching for particular keywords and images and so on. But I mean, what sort of array of data inputs are you using then? You have most extraordinary photographs that appear on your Twitter account of devices that you're building to capture this overtopping and so on. Are these are sort of custom machines, I suppose, for collecting the data? How do you go about building these novel sources of data for your modeling, I guess?
Yes, so our sensor looks a bit like a climbing frame or maybe a harp, I'm not sure. So it's a scaffolding rig with lots of wires laced up within it. And these sensors, well, the wires, when the waves pass through them, they have a contact signal, which sends a capacitance information to a logger. And we process that into the speed and the volume of waves that go flying over the top of the sea wall. Now we need information to know how big to build our climbing frame. So a photo is very valuable there. We also have been using camera information to try and work out which way the waves are going, so we can actually understand the data that we're collecting, because it's very rare that in the real world a wave comes in nicely, comes up to a seawall, hits it and go over. There's normally some wind blowing it along the seawall. So waves come in all sorts of different directions. There's a lot of noisy spray. So visual images are really helpful. But we're encouraging people to go and take photos for us, because we obviously don't want them to put themselves in harm's way. So we kind of rely on existing photos and cameras that have been installed by research scientists as well.
Yes, yes. Interesting. So, I mean, one of the other things I think your work is feeds into is this idea of trying to support rational, evidence-based policy decisions, and also trying to communicate with the public as well, and trying to make science understandable. And I just wondered if you had some thoughts on the role of digital approaches or digital technologies in achieving both of those goals, really, and how have you and your colleagues approached that, both with supporting policy making, but also communicating science to the public?
Yes, so we're still on a bit of a learning curve here. Initially, when we started this work, we were thinking about collecting information and then we could provide it to local authorities and that would help the design of a seawall. But now we're working in Dawlish with Network Rail, we realise there's a lot more opportunities. So they use a forecast and they decide when they perhaps need to put a speed limitation on a train or put a train on one track rather than using both tracks. So again, by having information about the waves passing over the railway line at Dawlish, maybe we could help the operation of the train system. So when we will know when overtopping actually stops. So rather than them having a fixed duration of closure or a speed restriction, we could actually monitor it. And if it's been okay for 15 minutes, you can send a message to say, well, it seems calm, so maybe an inspection is needed and maybe we could get the trains going sooner rather than waiting for that fixed time window. And then linking to the public, digital approaches have helped us a lot. We're currently creating an augmented reality coastal walk. So we're going to use our data and put it into a phone app that people can actually visualize stormy conditions when they're there on a nice sunny day. So the app will be GPS points that trigger something on your phone, so you can actually see the information, the stormy information that we're collecting when the weather is much nicer. So one of our apps is going to be Penzance and the other at Dawlish, and we're going to have voice of the sea and voice of the wind, because wind is also very important, as that's what blows the plumes of water over the sea defences. When they shoot up into the air and fall back, it's windy, they go over the coastline.
I'm just looking at some, thank you very much. I'm just looking at some of the questions coming in, and Bill has just posted an observation really that citizen science is critical part of the way forward, and members of the public, citizens can include, of course, academics, people who are interested in the environment, dog walkers, and so on, and they drive forward changes. You know, I think Bill, you're noting some various projects which where citizen science has played a role, and I think it's easy to see the public's interest in coastal issues like yours. Perhaps a little harder to have citizen science on glaciers and perhaps out in the oceans, but certainly for there's all sorts of examples of the use of citizen science to support support environmental science. Thanks, Bill, for just clarifying that. Very interesting. 2,500 sites in the UK with 3,500 volunteers in the UK. That's an extraordinary wealth of data. Imagine that's quite incredible. Jenny, I have to ask, as I have everyone else. It's only fair to put to you the drum roll question, and as you walk onto the stage or off, as whichever it is, which is your theme tune, and why is that?
Well, I thought Catch a Wave by the Beach Boys would be good for my current research, as I've been chasing waves for the last 4 years now. But also the songs about how great a feeling it is when you've caught a wave and you're surfing. And I was thinking, well, it does actually feel quite good when you're sat on the beach and you've developed a new prototype system, a wave goes flying through it, and the whole thing stands up and lasts and it doesn't fall to pieces. You feel that you've really succeeded in developing new innovations when that happens. So that's going to be my song.
Yes. So it's not quite as hostile as a glacier, but actually putting anything in the ocean is pretty testing, I think, especially on the with the kinetic energy that's being transferred to your climbing frame, as it were, that's strapped to the side of a wall. Is quite impressive that it's not been smashed to smithereens. But how many sensors are you typically using? Is it just one, or do you have a network of them?
We have a network. So again, I guess that means I need to work out how we classify a sensor. Is it just a climbing frame, or is it every individual wire? So our climbing frames have up to 18 wires. The ones that are out at the minute have 6. So we have 6 sensors on them. But we've also constructed the climbing frame in different setups, so it can be put in other locations. So on the wall of the railway line, also down the face of the seawall. So that might just have a single sensor or two sensors. So really, we configure it to fit the space we've got and meet the project partner's needs.
Yeah, Jenny, Lucy's just posted a very interesting point on the chat, which I'll relate to you, really just highlighting the importance of training and protocols, helping institutions to trust the data that's being captured. But when you have data that's coming from citizen science sources, the importance of metadata that goes with that records the origin, the provenance of the data, and training and protocols used. And Lucy's just noting that the EPA have a specific handbook for capturing quality assurance issues in citizen science. So that's an interesting observation. And in fact, Lucy, thanks for giving the link to that document. And so I'm wondering whether those sorts of approaches could be worth looking at when you're capturing your citizen science data. Also, Will has just noted, how do you get around distribution of citizen science data? It's easy to get where people go to, but you might need data in places that people don't go. And for example, during bad weather, because you can't rely on citizen science data. If the weather's inclement, which is actually when you need the weather data, suddenly your citizen science sources of data dry up. So how do you address that?
Well, that's why we're trying to make low-cost sensors. So when I was using Facebook, most of the photos were during daylight hours. They weren't there at night. So what if your storm comes through at night? So we need low-cost sensors that we can implement that kind of give you 24/7 data feeds, and that can provide your nowcast data. But it's really good to have citizen science to expand that data and add extra information. So at different sites, you can kind of balance the data sources differently. So it depends what works at each site.
Yes. I'm wondering if I might actually invite John to come and join us again. Hello, John. I'm in particular interested. Your earlier work was with the Met Office, and of course, I imagine the Met Office have extensive citizen science opportunities. There's so many amateur meteorologists out there. How did you handle contributions from the public, and how was that integrated into the whole? And is that something that can carry on now in your current work?
Yeah, I think it's really important actually to be able to access citizen science data. And in fact, I just posted a link. I don't know if you saw that.
Oh, yes, thank you. Yes,
the Weather Observations website, which I'm actually trying to remember. I think a lot of the data. Yes, I'm just checking one of the data points now. So a lot of that data is citizen science data, and the way it's treated is essentially that the person that sets up the weather site will have some interaction with the Met Office to understand what the basic minimum metadata is that they need to provide, as I understand it. But then when it's used with a higher error consideration because of its provenance, but the density of the data sort of makes up for the potentially lower quality. So that's essentially how you deal with the citizen science element of it. Is through properly documenting and then attributing error within your system.
Right, absolutely. So while I've got you both, look at it the other way around as well. Not just citizen science data coming in, but more about the sort of communication of the outputs of these models that we've been talking about, and trying to convey some of the issues that Matt actually raised before, sort of uncertainty. I mean, how do you are there ways of using digital technologies to try to convey difficult concepts like certainty to the public, to decision makers, to policy makers? How do you think we might go about doing that?
Sorry, who's the question to?
I suppose. Well, I mean, to both of you, but maybe I'll start, if I may, with Jenny, and then John, ask your view as well. So Jenny, I mean, how do How can you do that?
So I can think of when it's more policymakers, you can develop decision support tools, and then you can kind of explore what if type scenarios with interesting visuals. So you can look at a scenario, but you can have uncertainty going in either direction with kind of nice sliders on an online platform maybe. So you can explore potential scenarios. Maybe when communicating with the public, that's the more challenging one, because we're still kind of learning how to communicate our new science findings and get those shared with the public and raising awareness of the research we do. So how you then start to convey uncertainty around that, I think there's still quite a lot of challenges there, and it will probably come down to how we visualize data and show that, well, the environment is always changing and there are still unknowns that we don't capture. So there is a bit of an error from margin error on things.
I mean, I see. Thanks, Will. There's some nice questions coming in here. But John, if we're dealing with Jenny's drawing attention to the use of scenarios as a way of trying to help decision makers and policymakers understand different consequences of actions they might take, and just putting that together with our earlier discussion, what is the role of the digital twin in facilitating scenario-based modelling? I mean, one hears about being able to take a sort of a copy of the existing state of whatever it is you're looking at, peeling it off and then pushing it and prodding it in different ways to try and make things. So can digital twins bring a sense of realism to those scenarios that that perhaps you wouldn't have if you didn't have that framework of near real-time data coming in as well?
Yeah, they definitely can. And I think there are two ways they can do it. One is through canned data, stuff that's already simulations that have already been run. So the example being the CMIP data sets for the climate scenarios, where you can make them available through a digital twin and then have access mechanisms so that people can explore the data themselves. And I think that's really powerful to really sort of let people see the data themselves is key. The other way of doing it is allowing people to run their own scenarios, which means, and they're way too expensive. Most simulations are way too expensive to allow people to just arbitrarily go and do their own thing. But you can create emulators in digital twins that are much simpler variants of any sort of predictive tool. And I think there's a really important role there. And again, just get people trusting the data. They can start playing with that. So yeah, I think the other element that I think people are much more savvy around probabilistic information and the element of risk and probability than perhaps we've treated them as having in the past. I think the public can deal with probabilities, and I think we should treat them as such. And so we should give them sort of the idea of risk rather than individual numbers. I think that's a much healthier thing to do.
Thanks very much, John. Jenny, I see Will has just posted up a comment here about data that's privately held. So, for example, instrumented farm machinery and all the data that the fishing industry, and to perhaps take a slightly more oceanographic example, holds. How do you leverage this sort of privately, this body of privately held data? Are there safeguards? Are there mechanisms you can put in place to try and access that sort of data?
I guess you just have to ask nicely and find the right people. So normally in projects, we have a lot of project partners, and by showing them what we're doing and getting them to understand the value of working with us, normally people do share their data. But then we have to be careful to make sure we're not passing on their information. Yes. So the data we collect is generally freely available afterwards. But we build good relations with people and gather extra information and try to work with their decision support tools, their platforms, to feed our data into their existing management tools.
Thank you. I mean, and John, really sort of with your data center hat on, sort of the same question to you. We hear a lot of discussion about mechanisms like data trusts and so on, which are ways of head-on trying to address some of these issues where you actually place almost data in escrow for a greater good in a managed way. I mean, how do you think you could leverage this sort of private wealth of data that's out there as well? And what is the role of a data center in trying to do that?
Yeah, so I think there are two elements. One is corporate social responsibility. I think a lot of companies are really now hot on that, and I think if you can explain why they're able to articulate what they're doing for the broader good, I think they're open to sharing their data. But the other is having an infrastructure around the data that allows sensitive data to be managed effectively, and that's all about data management and data metadata and intellectual property being well covered. So I think there's a technological element, and then there's a sort of, as Jenny so aptly put it, if you're engaging with them, explaining to them what the benefit can be, and I think you will get a lot of this data.
Right. Well, this has been a fascinating discussion. Thank you both. I just wonder if it's possible, if digital technology will allow us to bring our first couple guests in as well. I don't know if that's possible, Will. Oh, there we go. Look at that. Fantastic. And Matt as well. There we go. Super. Very much. Do unmute yourself if you are muted. Well, thanks very much, all of you. I mean, we've been having an interesting discussion across this sort of arc of technologies, from capturing data in the first instance, whether it's from sensors or from citizen science sources, trying to precondition or massage that data, hold this, and then pass it to analytical techniques. And as a sort of an umbrella, we've had an interesting discussion about digital twins. I mean, I think it would be quite interesting, Jane and Matt, to hear your views about digital twins as well, and how this sort of emergent concept could and indeed does inform some of the planning and science work that you're doing. I mean, maybe Matt, to start with you, if I may, and then Jane, how are you using digital twins, and what's the role of them?
Yeah, we're very actively looking at digital twin technologies and what they can deliver in our area of science. I think for me, it's making use of, it's moving from traditional kind of modeling data assimilation to make use of new sources of data, real-time data, and understanding how they can be integrated into those modeling systems. I'm really keen to understand how you can bring that data together and to kind of dynamically understand the kind of certainty and uncertainty in models, so it can kind of help evolve the monitoring that you're doing where that's possible. So we talked about citizen science, so that's very mobile monitoring in that sense, and usually very done by people who are happy to contribute. And you can imagine that you can use the information that's coming in, as well as the digital twin sort of modeling aspects, to help provide that understanding of where the certainty and uncertainty is changing, and help direct where additional monitoring might take place.
Jane, one of the things about the digital twin is it's very finely calibrated to the particular environment you're looking at. So you can't really have a generic digital twin for all glaciers. But I mean, do you see a role for developing digital twins in your work at all?
It's something we probably think about in the future. I mean, we haven't really done anything like that because we've spent all our energy on trying to make the sensors, get the data back. Although we work obviously in glaciers trying to understand subglacial processes, our sort of basic philosophy is if we can get it to work in the glacier, it will work almost anywhere. And we would love to make something that, an instrument that can essentially swap its communication system. So, for instance, there are numerous 6 low pan, all sorts of other satellites, all sorts of communication systems, and we'd like to make a system where the system itself would automatically decide, it would sort of smartly work out how it can communicate, and then use those different systems embedded within it. So a sort of IoT, Internet of Things toolkit. So that would be our sort of part of that we'd like to develop a kind of smarter instrument that was more flexible. We've started we initially started with our IoT in the Cairngorms.
Right.
I managed to get data moved around the Cairngorm. So I suppose I would say probably digital twin is kind of the next step, but we haven't done anything yet.
I mean, we've heard some really great examples of the use of digital technologies in supporting environmental science. Jenny, I'm just wondering, are there areas where do you think digital techniques don't help particularly? Is it a force for good, or is it a force for careful consideration? What are your views in your work?
So I can't think where they don't help digitally. One thing they can't support is hands-on training. So if we are collecting low-cost sensors and trying to get other people to help deploy them and perhaps maintain them, digital supports all that communication, information sharing and visualization. But you still got to deliver some local hands-on training to get those sensors out there.
Yeah. Well, yes, Jane,
I would say the only thing that, the bad downside was that you actually still need to do field work, which is good. You've actually got to put them into the field and you've got to maintain them because they're quite difficult to maintain. So, I mean, for me, the great thing is that you've got this opportunity of doing field work. And as other people have said, by sending the data back live, people can visualize what's going on. So the general public can see the environment through webcams and live data coming back. And I think that's really vital because at the moment, society is going to have to make difficult choices about, reducing our carbon emissions, and getting people involved is one way of kind of helping with difficult decisions.
Interesting. Yeah. What do you think, John? Sounds like a good point there. I think you're muted.
Sorry,
feel free to unmute yourself.
My mouse was struggling to hit the mute button. I do think that's it's really important not to get too dragged down the digital is everything route. We need to have the whole combination, and I think that point about the fieldwork is critical. And we sort of we've seen that with the idea that sort of satellites can do everything that sort of happened in the Met community 20 years ago, and then they realised quite quickly that it's a combination of things. So we need to be really cautious about throwing away the baby with the bathwater.
Yeah. Okay, well, we're sort of drawing to the end of our allotted time, which is a great shame because I feel we could carry on for some time. But maybe what I'd like to do is just quickly whiz round you all, and sort of one final question just to get your thoughts really, and that is to do with sort of future challenges and the sort of direction of travel of digital techniques, and what is the future technologies? What will future technologies enable in our environmental science, and that sort of trajectory that we're on? So, Matt, if I may start with you, and what I'll do is I'll just whiz round everyone and ask this question, and then we'll sort of wrap up after that. So, Matt, what's the trajectory as you see it?
Well, thinking futuristically, I'm always a bit skeptical about machines just doing everything for us. But I think if we properly describe data with semantics, there's a lot that machines will be able to do to kind of streamline exactly what we need to our fingertips just when we need it, or into our research code in that sense as well. I think embedding all the information we have in our brains into these data streams, and then getting AI to kind of make use of that knowledge.
So the metadata is absolutely critical to understand the data. Thank you, Matt, very much. And Jane, what are your sort of closing thoughts on future trajectories?
I suppose I would say making instruments smaller, increasing standardization. So maybe you could use your phone to set up a sensor network, which you certainly can't do at the moment. And I guess making things just simpler for people. It's quite difficult for people who aren't experts to sort of work these systems at the moment. So.
Yes, yeah, simpler sounds good. And Jenny, unmute yourself, but I'd be interested in your sort of final thoughts on this as well.
I think we need to get our science into kind of navigation systems, maybe. So I'm thinking you've got your car sat nav, you route your direction, you've got your traffic light system if there's congestion. Well, I'd like there to be a traffic light system if that coastal road is flooded, don't drive around it, that type of thing. But it doesn't have to just be coastal hazards. With digital, we can integrate all the different environmental hazards. So maybe get landslide information, inland flooding, as well as your coastal flooding. So bring the disciplines together and get them into technologies that people are already using every day. So it just naturally evolves into their everyday ways of living.
John, are we going to have Microsoft Digital Twin in the future? Where's this all going?
Well, we may well do, but I think there are challenges, and skills has already been mentioned. I don't think we can overstate the issue of skilling up people in the digital area, but there is a fundamental change to the way we work that we've got to do as well. So at the moment, as a bunch of different environmental disciplines, we have developed our own infrastructure, our technological infrastructure and our metadata infrastructure quite separately, and integrating those things, both the physical architectures, perhaps in the cloud, but perhaps not, and also the information management frameworks is going to be a really fundamental challenge if we're going to do what Jenny's just said and have integrated systems. So integration, I think, is a challenge that we have in the next 10 years.
Yeah, so one of my colleagues and friends had a thought that NERC collects this absolutely vast bodies of data, not just oceanographic, but across the biomes, as we've discussed. You know, all the terrestrial data, the atmospheric data, the polar data. Do you think there'll ever come a time when machine learning approaches will be able to actually play across the entire body of data that that NERC have and hold? Is that an ambition? And if it is, how many decades, how many years ahead is that? That's a question for you, John. Yeah.
Sorry, yeah, if you're asking me, it is definitely an ambition. Of course it is. I think it's longer than NERC think. I'll put it politely.
Very good. Well, listen, I think that's just about all we have time for. Unfortunately, it would be great to carry on. I'd like to just thank sincerely the panelists, the four of you, Jenny, John, Matt, and Jane. Thank you so much for your time. I'd like to thank very much the audience. Indeed, there have been some fantastic questions coming in, and no doubt we'll capture those questions, and there's an opportunity to carry on a dialogue with our speakers and indeed with myself. One way you can do that, if you're interested, perhaps Gordon will advise with regard to the festival, but actually all five of us are linked to the NERC Constructing a Digital Environment program, and maybe someone will just pop in the chat here the website of the Constructing Digital Environment, and you'll notice in there are links to our forums and the email contacts and so on, and we'd love to continue that discussion with you. It's been a very useful discussion in the last hour and a half, exploring digital approaches and how they offer powerful means, I think, to address pressing environmental challenges to society and the environment. We've had some great examples, actually, of constructing digital environments. Always a most fascinating area to us. Now, I understand that Gordon will be making available, with his colleagues' assistance, the video of today's discussion, and that will be available on the Entangle website. And in fact, we will also hopefully have a copy of that on our Constructing a Digital Environment website as well. And so do come and meet us digitally. And I hope you, if you're able to, attend some of the many other fantastic events planned in the festival. And thank you very much for your time and your attention to this most interesting area. And I will finish with 1 minute to spare. So I think we're on time. So once again, thank you to everyone. And Gordon, I don't know if you're there and you want to conclude with any comments about the next set of things. I'll just pause for a minute if you, there you are. But I shall say goodbye and pass the floor, Gordon, to you. Thank you very much.
Yeah, and there's only really one thing still to say. A massive thank you to you, Steve. I think if Jonathan Ross is going to retire, then you might have a new career going forward.
Gracious me, why not?
Yeah.
Don't ask me what my theme tune is though.
Yeah, and as you said, there's lots more through the week. Look at our website for information. The next conversation will be Wednesday, and that's kind of coming top down from ecosystems, untangling ecosystems. And I'm hosting that, and I've learned a lot from how Steve has done this one. Thank you all, panel. You've been absolutely marvelous, and hope to see some of you on Wednesday.
Very good. Thanks very much. Goodbye, everyone.
Thanks. Bye.
Bye, everyone.
Bye.